Have you ever stopped and wondered why you can't find a cactus in the Arctic? Or why a polar bear wouldn't last a day in the Sahara? I mean, it seems super obvious, right? But the scientific reason behind it is actually one of the most fundamental rules in all of ecology. Today, we're diving into Shelford's law of tolerance. It's this really elegant principle that explains why, for every single living thing, there's a just right place to call home. Okay, let's get into it.
So here's the game plan. We're going to start with the just right principle itself. Then we'll actually visualize what that looks like using something called a tolerance curve. After that, we'll get into the big difference between adaptable generalists and those picky specialists. We'll also see how just one single factor can be the weakest link for survival. And finally, we'll put all the pieces together and see how this law fits with another major ecological concept.
All right, first things first. Let's get right to the heart of this thing. What exactly is this just right rule? Let's kick things off with a question that really cuts to the chase. A desert lizard, it can just chill in temperatures that would be instantly lethal for a fish that lives under polar ice. And of course, the opposite is true too. So what gives? Well, the answer is all about their specific, evolved limits. And here it is, the formal definition, cooked up by Victor E. Shelford, way back in 1911. It's such a powerful idea when you think about it. For any environmental factor, we're talking temperature, pH, saltiness, moisture, you name it, an organism has a very specific range it can handle. Where you find it in the world and how many of them you find is all dictated by these ranges.
Now this slide right here, this is the absolute genius of Shelford's law. It's not just about having enough of a good thing, like water for a plant, it's also about not having too much of it. See, too little water, the plant dies. But a flood? That'll kill it too. The conditions have to be just right, kind of like the Goldilocks story. That's the key takeaway. Both ends of the spectrum, too little and too much, can be total deal breakers.
So, how do we actually visualize these limits? Well, ecologists have this simple but incredibly useful tool for it. It's a graph, and it's called the tolerance curve. Right in the middle of this graph, you've got the sweet spot. We call it the optimum zone. This is where conditions are absolutely perfect. The organism isn't just getting by, it's thriving. Growth is at its peak, reproduction is going great, and this is where you'll find the most of them packed together. A great example is a freshwater fish like labio. It shows its best growth at that perfect, moderate temperature. Now, as you move away from that perfect center, you enter the zones of physiological stress. Life gets tougher out here. The organism can still hang on and survive, sure, but it's burning a lot of energy just to cope with conditions that aren't quite right. And because of that, its growth slows down, it doesn't reproduce as much, and the population starts to thin out. And finally, way out on the edges of the curve, you hit a wall. These are the zones of intolerance. This is the hard stop. The conditions, whether they're too high or too low, are just beyond what the organism can handle. It's game over. It cannot survive here, period. This is exactly why you'll never find a freshwater fish out in the super salty ocean. It's way outside its tolerance range. Okay, but here's a really interesting part. That tolerance curve we just looked at, it doesn't look the same for every single species. Some have a really wide, forgiving curve, while others have a super narrow one. This brings us to a cool concept called ecological valence. Ecological valence sounds a bit technical, but it's really just a term for asking how adaptable is this species? Does it have a wide tolerance for a bunch of different conditions, or is it a picky specialist with really narrow requirements? This simple question basically splits the entire living world into two major strategies for survival. And this table just lays it out perfectly. On one side, you've got your eurytopic organisms. Think of these guys as the ultimate generalists. They have a wide tolerance for a ton of different factors. Cockroaches, humans, we're classic examples. We can pretty much survive anywhere. But on the other side, you have the stenotopic organisms. These are the specialists, and they have a very, very narrow tolerance range. Coral reefs are the perfect example. They need the water temperature, the salt levels, and the water clarity to be in this tiny, precise little window. We can even apply these same labels to specific factors. So an organism that can handle a wide range of temperatures, like our desert lizard, is called eurythermal. But one with a super narrow temperature tolerance, like a polar ice fish that's adapted to live only in near-freezing water, is stenothermal. So you see, this whole idea of wide versus narrow tolerance applies across the board to all kinds of environmental factors. Okay, so every creature has all these different tolerance ranges for different factors. How do they all work together to decide where a species actually lives? Well, it often comes down to the single weakest link in the chain. See, an organism has to deal with everything at once.
temperature, water, nutrients, pH, all of it. But a lot of the time, its final location is decided by the one single factor that it has the narrowest tolerance for, or the one factor that's furthest from its happy place. So even if a plant has the perfect soil and all the sunlight in the world, if the temperature's outside its tolerance range, it's just not going to be there.
This leads to a really important question that tackles a common assumption people make. When we see an empty patch of ground, our first thought might be, oh, some other plant must have won the battle for that space. But is competition really always the reason?
And the answer is a definite no. This is such a critical distinction to get. So often, a species is missing from a spot not because it got outcompeted, but simply because the physical or chemical conditions of that location fall into its zone of intolerance. The soil pH might be way too acidic, or the temperature might be too high. It's a physiological barrier, not a biological fight.
Now to get the full picture, it's really helpful to see how Shelford's law connects to another huge idea in ecology, Liebig's law of the minimum. You can think of them as two sides of the same coin.
Looking at them side by side really clarifies things. So Liebig's law, that focuses only on the minimum requirement, like the one nutrient that's in the shortest supply. It's only concerned with deficiency, not having enough. But Shelford's law is much broader. It looks at the entire range, from the minimum all the way to the maximum, and it gets that both not having enough and having too much can be limiting. Plus, it applies to every environmental factor, not just nutrient.
I love this quote because it just sums up the relationship perfectly. These two laws aren't fighting each other, they complete each other. Liebig's law tells you about the absolute lowest limit. That's the floor. Then Shelford's law comes along and says, yep, that's the floor, but let me also show you the walls, the upper and lower limits, and the ceiling, which is where things become toxic or excessive. Together, they build the entire room that a species is able to live in.
So let's end with this thought. We've seen how every single species has this optimum just right zone where it does best. Now think about how we're changing the climate, altering the pH of our oceans, and completely modifying landscapes. We are fundamentally shifting these environmental factors all over the planet. So the real question to chew on is this: how are our actions pushing countless species out of their comfort zones and into zones of stress, or even worse, into zones of complete intolerance? It's a pretty powerful way to look at our impact on the world, isn't it?